Okay, welcome back to COSC 2325. This is Chapter 6, Part 2. In this video, I'm going to cover comparison instructions and conditional jumps. So we're just going to cover these two sections. Okay, so the CMP instruction compares the destination operand, so destination to the source operand. It is a non-destructive subtraction of source from destination. The destination operand is not changed. So here's an example. If we move 5 into AL and we compare AL to 5, AL is going to be equal. The destination is going to be equal to the source. So the 0 flag is going to get set. So with the compare, what you have to remember is which flag gets set. And that is something that you're going to have to commit to memory. So maybe make yourself some notes for this part. So compare, equal destination, equal source, 0 flag gets set. If destination is less than the source, the carry flag gets set. So destination, AL, is 4. Is 4 less than 5? Yes. We set the carry flag. If the destination is greater than the source, so AL is 6, 6 is greater than 5, both the 0 flag and the carry flag get cleared. The comparisons shown here are performed with signed integers. So here it says, is destination greater than source, which it is. 5 is greater than a -2. Since 5 is greater than -2 and it's looking at signed numbers, the sign flag is going to equal the overflow flag. So both of these are going to be equal to one another. In this one, if the destination is less than the source, the sign flag is not going to equal to the overflow flag. So destination less than source, sign flag is not going to equal overflow flag. Okay, so the CMP instruction, we're going to be using it with conditional jumps. So let's take a look at that. Conditional jumps are based on specific flags, equality, unsigned comparisons, and signed comparisons. We're going to look at some practical applications. We're going to also look at how to encrypt a string and look at the BT instruction, which is bit test, meaning testing to see if a bit is set or not. Okay, so jump on condition. There's going to be a lot of jump on condition instructions that we're going to look at. And these you do not have to memorize, okay? So a conditional jump instruction branches to a label when specific register or flag conditions are met. So these are jumps based on specific flags. And you do not have to commit all these to memory. There's going to be certain ones that we use more than others that you'll slowly just start to understand why they get set, which ones they get set. They're pretty easy to remember though. So this is jump if 0, jump if not 0. So since we're talking about 0, then of course the 0 flag is going to get set. Jump if carry, jump if not carry, carry flag we're going to be looking at the carry flag. Jump if overflow, jump if not overflow. The overflow flags are checked. Jump if signed, if not signed, the sign flags are looked at. We haven't done anything with the parity flags, but there's jump on parity being even and not parity, meaning odd number of parities. So PF1, PF. So looking at the parity flag here. So the flags are not too hard to remember. The mnemonics, I think, are pretty simple to remember too, since this is Z for zero, not zero, C for carry, not carry, O for overflow, NO, and then sign, not signed, parity, not parity. So I think these could be something that you can easily look at and be able to tell what it is, tell what flags are being checked, and really you don't, I mean, it's just common sense, so you don't have to really commit this to memory. As far as the jump ranges with the 86 processor, there's not a specific number of bytes that is going to be used to jump, so we can jump anywhere in memory. Prior to the 386, jump must be within negative 128 plus 2 positive 127 bytes from the current location counter. But we don't have to worry about that. So this is jumps based on equality. So we have jump if the left and the right operand are equal. So jump equal, jump not equal. They're not equal to one another. Jump if the CX register is equal to 0. So CXZ, so CX0. Jump if the ECX register is equal to 0. So here we're looking at the registers, and here we're comparing, is the left equal to the right? And the way we're going to compare is by using the CMP instruction. And we'll look at some examples in a second. These are jumps based on unsigned comparisons. So these are a bit harder to remember than all the rest. So JA, jump if above. So basically saying, is the left operand greater than the right operand? So is it bigger? Jump if not below or equal. So it's the same as JA, but it's the not below. So it's the opposite. And then jump AAE, jump if above or equal, so greater than. So above, just think of it greater than, like if, let's see, 10 is greater than 9, so 10 is above 9. It's the way you can think about it. So jump if above or equal. So is the left operand greater than or equal to the right operand? This one's just like this one. This is just not below. So it's just saying not less than or equal to. So it's the same, but with a not. And then JB, jump if below. So if left operand is less than right operand, and this J not above or equal is the same as JB. And then JBE, jump if below or equal. So is it less than or equal to? And then J and A, jump if not above, is the same as less than or equal to. So jump if not above, jump if below or equal to, same thing. Depends how you think or how you want to show it on the screen. So these are actually these are not the ones I was thinking that are hard to remember. I think for me, these are the hard ones. In this one, you just have to remember A means above, B means below. N is not, E is equal. Above, not below, equal, above, equal, not below, below, not above, equal, etc. So this is JG, so jumps if greater. So now we're looking at sign comparisons. So is the left operand greater than the right operand? Not, this is the same as this one. Greater than or equal to, and not less than, which is the same as GE, less than, not greater than or equal to, less than or equal to, not greater than. So you just have to remember which ones are for signed numbers and which ones are for unsigned comparisons. So maybe thinking above and below, those are unsigned. And then using the words greater than and less than, you could think of it that way as for signed. So greater than and less than, so greater than is the same thing as above. Above is for unsigned, and G greater than is for signed. Then below is the same thing as less than. So left operand greater than right operand is the same thing as left operand greater than right operand. Up here you're using JA because it's unsigned. Here you're using JG. So whatever you want to do to figure out how to commit that to memory, you can do that. Okay, so let's look at some applications. So here, the task is we want to jump to a label if unsigned EAX is greater than EBX. So the first thing we want to do is use compare. And remember, compare is going to give us if it's greater than, so oops, keep pressing that. Compare EAX to be EBX. So jump to a label if unsigned EAX is greater than EBX. So here, when you compare, remember if it's equal to, on the compare, let me go back to this. Yeah. So if it's equal to, the 0 flag is set. If it's less than, the carry flag is set. And if it's greater than, both the 0 and the carry flags are set. Okay. 0 carry. And then 0 carry flag. So, or these are cleared, sorry. These are set, meaning they set to 1. These are cleared. So when we go here, we're using JA. JA means jump above. So if, not jump above, but is jump if EAX is above EBX. So if EAX is greater than EBX, above it, then jump to larger. So go back to JA here. JA is used for unsigned comparisons. We're comparing if the left operand is greater than the right operand. So if you know that if EAX is greater than EBX, both the 0 flag, Remember, both the zero flag and the carry flags were set to 0. So what I want you to think is this is not anything that you have to be concerned about, but this instruction JA, what it does is it checks those flags, right? It's checking, so JA checks the 0 flag and it checks the carry flag. And if both of those are 0, because the comparison set them to 0, if this is greater than this one, then it jumps to larger. So that's happening. That's not anything that we have to worry about, but that's what that is. That's what JA is doing. And so we don't have to worry about what the flag is because we're not physically checking the flag. JA is checking the flag. All right. So here we're doing the same thing, except we're comparing signed numbers. So this is signed. Therefore, we have to use jump on greater. This is just a label somewhere that we jump to, okay? So it compares them if EAX is greater than EBX. Again, we're going to, now here, because we're comparing sign numbers. So remember that if you compare sign numbers, it's a little bit different. So if we're looking to see if the destination is greater than the source and we have sign numbers, then the sign flag is going to equal the overflow flag. Once again, you don't have to worry about that, but that JG instruction, that's what it's doing. So it's coded to check to see if these flags are equal to each other. And if they are, it jumps to the label. But we don't have to worry about that. And then what I like you to do is try these out at home. So using, go ahead and open Visual Studio, assign a value to EAX, assign a value to EBX, make EAX greater than EBX, like you could say EAX equals 6, EBX equals 5, and then create a label called larger. So you're just going to say larger colon, that's the label. And then if you wanted, if you're using the Irvine library, you could print a message just to test it. So it would be like this, say larger colon, and then you could write a message to the screen, like, yes, the number was larger, EAX was larger or something, however you want to do it. But this is the label right here. Just has a colon at the end, and it matches this. Does not have to match in like capital and lowercase letters. So it doesn't have, it's not case sensitive. So try it out just so you can see it. All right, this one, it jumps to label 1 if unsigned EAX is less than or equal to value 1. So it jumps, so we're on signed, so we're looking at the instructions we're using are that have A or B above or below. So jump if below or equal. This one is signed, so we're looking at greater than, less than. So this is jump less than or equal. Again, you can try these out. L1 is a label. So you got to create a label to jump to. Here says compare unsigned AX to BX and copy the larger of the two into a variable named large. So what they do first is they make bx the largest. Now we don't know if bx is the largest. We just have to set something to be the largest. So we've set bx to the largest. We compare ax and bx, and we jump not above. Remember, jump not above is the same thing as less than or equal to. Let me double check on that. Jump not above. Maybe it might just be less than. Jump not above. NA. Yeah, so it's the same thing as jump. Okay, so it's not. It's the same thing as less than or equal to is down here. Okay. So jump not above. So if AX is not less than or equal to BX, or you can think of it as if AX is less than BX, then we're going to jump to this next label. Otherwise, we're going to skip the jump and we're going to assign AX to be the largest. So hopefully that makes sense. Take a look at it. It should make sense to you. Same thing here. We're going to compare them, and we're actually looking for the smallest. So make AX the smallest, compare them. If BX is if BX is greater than AX, right? Okay, if not BX greater than or equal to S, so destination, so it's the opposite. I hate the knots. So it means is BX less than or equal to AX. If it is, okay, it was just getting really late. It's the smallest. Oh, we're doing smallest. I was thinking we're doing largest. Okay, so if BX is bigger than AX, I mean, excuse me, smaller than as in bigger than AX, we're going to jump to next. If it's smaller than AX, we're going to move BX to be the smallest. Okay, jump to label to L1, so label called L1. If the memory word pointed to by ESI equals 0. So we're comparing whatever ESI holds. So whatever number it holds, we're comparing it to 0, and we're jumping if they're equal. And then here, we jump to label 2 if the double word in memory pointed to by EDI is even. Now, if you remember from the last lecture, to find if a number is even, you use either and or test. And is going to change the destination. Test does not change the destination. And you mask just the very first bit of the number. So by doing that, we're going to know if it's an even number or an odd number. So we add 1, or not add 1, but we mask it, and then we'll be able to tell if it's an even number or not. And the reason we can tell if it's an even number is because if you mask the very first bit and it makes, so if you have 0, 0, 0, 0, 1, and what you get, the result that you get is all zeros, the zero flag gets set to 0, and it means it's an even number. So by doing 0, 0, 0, 0, 1 to any number that is even, it changes that binary number to all zeros. So let me just show that to you. So for example, let me pick an even number, binary even number. Let's do 2. Okay, so we know 2 is it's an even number. So remember, this is position 0. It's worth 1. This is worth 2. This is 2 to the power of 0, which is 1. 2 to the power of 1 is 2. To the power of 2 is 4. This is 8. To convert it to decimal, you do 1 times 0 is 0 plus 2 times 1. So this equals to the decimal 2, okay, which we know is an even number. So if we do test 1, what we're doing is, just as a review, we're doing this. Oops. And it's like doing an AND. So test is like an AND. We're ANDing it with 1, but with AND, it actually changes the result that we get here, gets copied to here. There's a destination. With the test, nothing happens to the destination. So here we say 0 and 1, so false and true is false. True and false is false. False and false, false and false. All these become zeros. And this is going to happen every single time you have an even number. So this right here sets the 0 flag to 0. JZ is what JZ checks the 0 flag. And if the 0 flag is set, it's going to jump to L2, which is what happens. See if I can erase this. Look at me go. And let's see if I can go to the next slide. There we go. I want to put back my pointer. How about I put back my pointer? Okay. Jump to label 1 if bits 0, 1, and 3 in AL are all set. Solution, clear all bits. So we're going to clear all the bits except bits 0, 1, and 3. Then we're going to compare the result with 1, 0, 1, 1. So this is bit 0, this is bit 1, this is bit 3. And if they're equal, so if AL is equal to this right here, this pattern, then we're going to jump to L1. Okay, so the first thing we do is AND. So let's go ahead and do this one here. So we have 4 zeros, 1, 0, 1, 1. And what we're trying to clear is bits 0, 1, and 3. And the way we clear those is by putting a 1. Okay, so why a 1? So let's just, I'm just going to do, by the way, I'm just going to do these last 4. Okay, so 1, 0, these last 4 bits, 1, 1. And I'm going to say that AL has Let's say that AL has 0, 1, 1, 0. So this is AL, this is the destination. By the way, because we're ANDing it, AL is going to get modified, right? So AL is going to get changed to whatever this is down here, whatever this result is. So we're doing AND. False or true is false. True or true is true. True or false is false. False or true is false. Okay. So what we have left is 0, 0, 0, 0, 0, 0, 1, 0, which is not going to equal to this right there, right? But let's just take a look at this. So whenever you put a 1, if you have a 0, it becomes 0. If you have a 1, it stays a 1. So if you have a 1, it stays a 1. Otherwise is a 0. So the only bits that we actually changed was the third bit. It changed from a 1 to a 0. So anytime that you have the AND with a 0, you don't change, you're not changing any of the bits. The only time that you change it, oh, sorry. So wrong. This one is, let's see. Okay, so in this particular case, I'm now confusing myself. So I cleared out bit number 3, 0, 1, 2, 3, right here. And then 0, 1, and 3 in AL are all set. Okay. Mm, 0. So let's make it 0, 1, and 3 all set. So this makes a little more sense. So 0, 1, and 3. Okay, so that's what we're actually getting. And we want this answer here to look like that, so that when we compare it, then we jump if they're equal. So clear all the bits except bits 0, 1, and 3. So to clear it, we actually use zeros to clear it. So all these right here, all these zeros, clear everything, and the ones keep it the same, which is what I was trying to say. So if you want to clear a bit, you AND it with in whatever bit location with a 0. So clearing a bit, you want to AND it the bit location with a 0. So if you want to clear just bit 1 or bit 0 right here, then you would make this a 0 and make all these 1s, and that would clear that one. So if I had 1, 0, 1, 1, and I want to clear just bit 0, then I would AND it with 1, 1, 1, 0. So I ended with this. So 1 and 0 gives me false. This gives me true. This gives me false. This gives me true. So this bit did not get changed. This bit did not get changed. This bit did not get changed, but I did clear my first one. So to clear it, we clear it with the zeros. Okay. That's everything. All right, so here's some things that I'd like you to do to practice. So pause the video, practice doing these. And then once you do those, so the first one says, write the code that jumps to label 1 if either bit 4, 5, or 6 is set in the BL register. So so in this one, it was checking to see if they're all set, but this one is an OR. So it's a little bit different. It's not, you don't want to know if they're all set. You just want to know if one of them is set. Okay. In this one, it jumps to label L1 if bits 4, 5, and 6 are all set. So that's the same one that we just did right now, but with bits 4, 5, and 6. So it's like this one, but 4, 5, and 6. Here, you write the code that jumps to label 2 if AL is an even number. So remember, to check if it's an even number, you're going to, you're ANDing, or you could use test. Probably test would be better. The very first bit, bit 0. End it with a 1. So it's going to look like, oh, here, no. It'd be like this. Except we're not using double book pointer EDI. You could use test 1. You are using AL. Write the code that jumps to label L3 if EAX is negative. So this one, you're looking at the EAX register. And remember, for this one, you have these right here. So jump if EAX equals 0. But we're checking actually if it's a negative number, if EAX is negative. So that's not going to work. Let's see. If EAX is negative, so that would be signed. And so we're looking to see if EAX is less than 0. And then you would use EAX is less than 0. Yeah, because EAX is signed, then you want to use one of these and check to see if it's less than 0. I'll just give you that hint on that one. Then write the code that jumps to label 4 if the expression EBX minus ECX is greater than 0. Okay. All right, this right here is just some code I want you to type and try it out. So the following loop uses the XOR instruction to transform every character in a string into a new value. Remember the exclusive OR, it if the two bits are, if the two bits that you're comparing are equal to one another, either 0 and 0 or 1 and 1, then it sets those or changes those to false, and or gives you a false. Everything else gives you true. So it's using the exclusive OR to transform every character. So run this, take a look at it, see if you can understand this code. And then the last instruction that we're going to look at is the bit test instruction. So you have BT is the mnemonic. You have the bit base, comma, and N. It copies bit N, so this is going to be a number. Copies that bit from an operand into the carry flag. So for example, if you say BTAX9, it's going to look at AX. It's going to look at bit 9. Whatever is in bit 9 is going to get copied to the carry flag. Now, bit 9, it's going to be either a 1 or a 0. So this is going to jump on carry. Remember, jump on carry jumps if the carry flag is set to a 1. So if bit 9 is a 1, it's going to jump to L1. Bit base may be a register like AX, or it can be a memory location. It can be a variable. So this right here can be either a register, a 16-bit register or memory location, or a 32-bit register or memory location. It cannot be anything less than that. And then N, this number can be a constant, just like here, right? Immediate, we call it immediate number constant. So like a 9. It can also be a register. It cannot be a variable. So N can be an immediate register, an immediate value, or it can be a variable. God, I keep saying that wrong. N can be an immediate value or a register, 16-bit register or 32-bit register. So like this could be AX or EAX or a number like 9. This could be variable or the registers. Okay, that is the end of this section. Make sure you take the time to type in all those examples and then try to figure out how to do these 1, 2, 3, 4, 5 small little programs, and I will post the answers to these. Probably not tonight, but I will post them. Okay. All right, guys, email me if you have any questions. Thank you.